Welcome to this presentation of the Cognitwin Digital Twins demonstrator. My name is Michael Jacobi from Fraunhofer ISB, and this demonstrator was a joint effort from Fraunhofer and Nisatec. Let's start with an overview of the demonstrator. In our scenario, we have two companies, Company A and B. Company A has a machine equipped with a temperature sensor that is sending its data via MQTT. We want to create a digital twin for the machine and add some cognition service on top. Parts of the digital twin shall be accessible by Company B through the access and usage control provided by the International Data Spaces, or short IDS. Now, how to get from our machine in Company A, shown in the top left, to the user in the Company B, shown in the bottom right. In this video, we will answer this question step by step. For demonstration purposes, the machine and sensor are simulated by a data generator. The next step is to create a digital twin for the machine. We will start by creating a digital twin model. In Cognitwin, we are using the Asset Administration Shell, or short AAS standard, defined by the platform Industrie 4.0 consortium, which is publicly available free of charge. On the left, you see a highly simplified version of the AAS meta model. The core element is the Asset Administration Shell, which represents one asset and can contain multiple submodels. A submodel can again contain multiple submodel elements, which can be of different types, for example property or operation. Although there are plenty of other submodel element types in the standard, we are focusing on properties in this demonstrator. Now we need to model our concrete digital twin based on this meta model. We're going to do this using the JSON format. Here we see the JSON representation of an asset. Each element of the AAS requires a local identifier called ID short, and some elements also require a globally unique identifier. Each element also has a model type. In this case, the model type is asset and can optionally have a multilingual description. The representation of the Asset Administration Shell is straightforward, containing again identifiers and a link to the asset we just defined, as well as links to the submodels we're going to define in the next step. Our submodel is called status and contains two submodel elements of type property, temperature of type float and overheating alarm of type boolean. Now that we've finished modeling our digital twin, we want to actually create a running digital twin service. For this, we are using the Fraunhofer AAS Tools for digital twins called FA³ST. This is a Java library that allows easy and fast creation of digital twin services and is extensible in many ways. This code shows all that is necessary, of course besides a previously created model, to create a running digital twin service that can be accessed via standardized APIs. First of all, we read in our model to create a so-called environment. After that, we can use the convenient Fluent API to create and configure an AAS service by setting the environment, data access implementation, and endpoint implementation. Standard and the library allow for using different endpoints, for example HTTP, OPC-UA, or others. For the demonstrator, we are using an HTTP-based endpoint that needs to be configured with a port to listen on and some mappings defining the offered functionality of the AAS. In this case, we are saying that the digital twin shall support all operations related to submodels and to the Asset Administration Shell. Finally, we can call the start method, which boots up a web server on port 8084, offering the standardized HTTP AAS interface. We can now verify that our digital twin service is working as expected by opening the corresponding URL in the browser. As a result, we get back the definition of the AAS which we just defined. Coming back to the demonstrator overview, we now have a running digital twin which provides a standardized HTTP API for accessing it. However, we have not yet connected it to the actual machine. To do this, we can add a few more lines of code to actually connect the digital twin to the machine data via MQTT. Once we successfully restarted the digital twin, we can now access that actual sensor data via the digital twin API, for example, by using our browser. As expected, we see the constantly changing value from the sensor. The next step is to integrate cognition services with the digital twin. For this, we integrated the digital twin with the open source software Apache StreamPipes, which provides a user-friendly visual editor to create stream processing pipelines. In this demonstrator, the cognition service will be to detect overheating events and create some corresponding overheating alarm. To make this as user-friendly as possible, we created a new digital twin data source and data sink for Apache StreamPipes. Now let's switch over to the Apache StreamPipes UI. The first step here is to create a digital twin data source. For this, we click on Connect and then choose the AAS over HTTP adapter. Here we have to provide the root URL of our digital twin we just created, as well as an polling interval. In the next dialog, we are presented all the available properties of the digital twin as previously defined in the modeling step. We can now rename or remove properties or even specify additional data transformations. As we want to compute the overheating alarm with our pipeline, we remove it here as an input. In the last step, we can name the adapter and start it. When we now switch to the pipeline editor view, we see our just created machine AAS as an input data stream that we can just drag and drop into the pipeline. Now we could do any kind of computation or stream processing that is supported by StreamPipes. In our case, we will use a custom data processor that is using the City Complex Event Processing engine to detect trends. After connecting the digital twin data source with the data processor, we are asked to configure the data processor. We want the alarm to be raised when the average value of the temperature property over the three last values is greater or equal to 70, and the output property should be named overheating alarm. Finally, we can switch to the tab Data Sinks and choose the digital twin HTTP data sync component. Again, after connecting the components, we're asked to configure the data sync. Here we only have to provide the URL of the submodel and check that we want to send the overheating alarm property to the administration shell. Now our pipeline is finished and we can save and start it. Once the pipeline is running, we can check via the browser if it's working. Once the temperature is high enough, this value should change to true. Now that our pipeline is running, we are generating overheating alarms when the temperature gets critical. Our simple cognition service may seem trivial, but in real-world applications, this processing step could be much more complicated and, for example, include using physical models or neural networks to detect or predict certain events. The last part of our demonstrator tries to show how this data can be accessed by another company while enforcing access and usage policies. To realize this, we're using the International Data Spaces IDS standard. This requires each communicating party, here company A and company B, to have an IDS connector running. On provider side, which is company A, we have a policy defining usage and access control based on the IDS implementation MyData. Consumer side, which is company B, We need the application to run within the IDS connector so that company B can only access the potentially sensitive data of company A via that verified application. At last, we can now open the app that the company B uses to display the data. Unfortunately, we will not able to see how data access and usage control is enforced because that happens in the background deep inside the technical systems without any user interface. This is the application the user in company B uses to display the status of the machine which belongs to company A. On the left side, we see the live temperature, and on the right side, the overheating alarm that is triggered once the temperature reaches the critical value of 70 degrees for at least 3 consecutive measurements. Once the temperature falls below that critical value, the alarm is turned off again. Thank you very much, and I hope you enjoyed this demonstrator.